Alright, so we're going to look at exponential modelling, and this is an extension of the solving for exponentials. We're going to use some log laws from time to time, but mainly it's around the solving and sketching of exponentials that we've been doing the last few lessons. The first thing I want to highlight is that this takes two forms generally, and the letters might change. It might be N, it might be NO, it might be Q, QO, C, whatever. It doesn't matter. It'll have, I'm just going to use a final amount, and I should have written that down, a final amount, an initial amount, and something to the power of t. Now they come in two fundamental forms, either b, but b would be a number like, for example, 0.8 to the power of t. Happy with that? And if I started with 1,000, if we're using a half-life example, 1,000 grams, I'd put that in as my initial amount, which means my independent variable, which is normally my x, is my t. So my time is my independent variable. Why is time an independent variable? Usually. Can you do anything about the time? So time is often the independent variable, and the dependent variable is often our final amount, which I'm going to write over here because I forgot to earlier. Whatever unit for mass or whatever you're dealing with, mass, number of atoms, whatever you use for your initial amount, that's what you're going to be left with in your final amount. Now I want to talk about these two things because they are the same thing. And I want to specifically focus on a little letter E. E represents Euler's number. Now Euler's number it's a special number like pi. You don't exactly know why it's special right now because most of its specialness aligns with calculus and you haven't done any calculus yet. But I can tell you that you're going to be seeing a whole lot more of E in your time. All you need to know is that E is a positive number. It's close to 3. It's 2.71. So much like pi, if you ask an engineer, what's Euler's number? 3. What's pi? 3. Euler's number is a special number and we use it often with exponentials. Now I can replace b with e to the power of k. So instead of using b, like I've been using in the past, I can use e to the power of k. And that allows us to do stuff with rates of change. I want to provide an example of that very, very shortly, but just understand that you're going to be coming across both of these. If it doesn't tell you, because often it'll give you a model, it'll tell you this is what the model looks like. If it doesn't give you an initial value, you can pick and choose whichever one you'd like. Happy with that? So I'll run through what these values mean. A0 is our initial amount, A is our final amount. B, that's our growth or decay constant. If in this form here, where it's just got b to the power of something, if b is greater than 1, it's a growth function, which means it does that. If b is less than 1, it's a decay function, which means it does that. Examples of growth would be things like disease. So if you look at COVID, for example, the way that COVID spread throughout the world, that would be an example of exponential growth. Whereas if you're looking at half-lives or things like that, that would be exponential decay. Or like the way that drugs wear off in your body, that's an exponential decay oftentimes. To give you an example of what an exponential decay would look like, if I walk half the distance, you can leave this room, for example, if I was to say, Ethan can leave this room when he walks out the door. The only caveat is he has to walk half the distance between him and the door and stop. Does Ethan ever leave the door? No. He gets very, very close to the door. He's pretty much standing at the door, but he never actually leaves the door. That's an exponential decay. He does most of his distance in the first stop. Half his distance is done in the first stop, correct? And then he progressively gets less and less and less until he approaches the door. What's another name for the door in this scenario? Asymptote. Asymptote. Very, very good. So, we're almost always using time as our independent variable. The A, that might be an amount of weight, it might be an amount of atoms, it might be an amount of money, it might be an amount of bacteria, it could be all sorts of things. But that doesn't matter. Sweet. So let's talk about an example of this. Also, side note, when modelling, as we would already be aware, as per our last exam, we were asked to create a model for a piecewise function. And what skill do we need to rely on? Simultaneous, as we do with modelling of exponential. Why is that often the case? Well, when I'm asking you to model, what am I usually giving you? I'm giving you an equation form. I'm saying, the equation looks like this. And then what else do I give you? Sum, starts with D. Sum. Oh dear, that's concerning. Okay, what else am I giving you? When I give you when I give you a model, a mathematical model, I usually say, here's the function, and I give you some data or information about it. What's usually the data that I give you about a function or a model? I'll say it goes through the coordinate 0, 3 or whatever. And what do you know? When I give you that data, what do you know? When x equals 0, y equals 3, and we can start using that information to identify what the unknowns are, which is simultaneous equations. Cool? So get used to using simultaneous equations. We're going to go through an example of one that's kind of we'll go through one. Let's go through one here. We've got a wealthy art lover has a particular work that increases in value 12% every year. He decides to purchase it. So this is an example. The initial amount is $175,000. So we write that down.